tens complement, we said that a nice complement is when I give you 2. Oh, really? So this is the maximum I can. Okay, so a nice complement is when I give you something like 2. Okay. So when I give you something like 218 minus 512, if you have to take the nice complement, so it's going to be 218 plus nice complement of 512 plus 1. And that is going to be 481 plus 1, which will give us 482. Then when you worked on it, you're going to get 2 plus 8, 0, 0, then 7. I don't know. Maybe you can do it later on. So we talked about this the last time, that's the nice complement, and that algorithm helps us to find to perform subtraction in a much more efficient and simple way. Now, one personal side note that I would like to add is that this is one particular algorithm. If you can also discover a more efficient one than this, then in the next few 10 to 20 years to come, it will be your algorithm that we will be teaching in classrooms. So you should also let your mind explore. Maybe you can find something out of it. Now, how do we apply these in binary? In binary, much the same way. Let's say I give you 1, 1, 0, 1 minus 1, 0, 1, 0. Then I say I'll find the complement of this. Perform this subtraction using the complement method. Similarly, what you're going to do is that you're going to find, so it's going to actually be okay, so we are going to do 1, 1, 0, 1 plus. In this case, we are going to take 1's complement, not 2's complement. Sorry, not 9's complement. So we take 1's complement of the negative number, right? And when we say 1's complement, it means subtract each of the elements from 1. So you see 9's complement, we subtract each of the elements from 9. In 1's complement, you subtract each of the elements from 1, right? And so 1 minus 1 is 0. 0 minus 1 is 1. 1 minus 1 is 0. 0 minus 1 is 1. So technically, when I say find the 1's complement, it means invert the number, right? 1's complement of 1, 1, 0, 1, 1 would be inverted, right? It's simply going to be 0, 0, 1, 0, 0. So you don't waste time. You just invert each of the bits of the element. Then after we find the 1's complement, just like we did for the 9's complement, we will add 1 to it. Right, so this is going to give us 1, 1, 0, 1 plus. So 1, 1, 1 plus 1. So 1 plus 1 is actually 0. Remember 1, we carry it forward to this one. Then 1, then 0. And then we are going to get, what do we get? We are going to get 1, 1, 0, 1 plus 0, 1, 1, 0. And this gives us 1, 1. So 1 plus 1 is 0, and then 1 and 1, 0. Is that right? So you see that over here we have the carry with extra carry in front, which is 1. So it tells us that so we are going to discard it. That means that 1, 1, 0, 1 minus 1, 0, 1, 0 is equal to 0, 1, 1. After we discard the extra carry bit. Please, do we understand? No one should say no. Do we understand? Yes, do we understand? Okay, so let's try this. Try this, the whole class. You're going to try this. So in the exam, I can give you this question. I would say that given that x is equal to 1, 1, 0, 1, 1, 1, 0, 1, and then y is equal to 1, 0, 0, 1, 1, 1, 0, 1, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Then I'll tell you that use ones and twos complement to evaluate a x minus y and then b y minus x. Please try this. Let me see if you can. Try this and then let me have your answers. You have 3 minutes. So you're doing a x minus y and then y minus x minus y and y minus x. So Kingsley is saying that my screen hasn't updated. Please, who else is having the same problem? So Kingsley, it just okay. So I'm typing it in the text box. X is 1, 1, 0, 1, 1, 1, 0, 1. Y is 1, 0, 0, 1, 1, 1, 0, 1. So you're finding a yes. Yeah, please talk. Yeah, your hands is up. Yes, talk. So I've shared it in a text box. Amankwa, yes, your hands is up. Please talk. Amankwa.
Mine too was the same, but it has been solved.
Okay, so now it's showing here. It's showing on your screen. The network is very, very, very terrible. Very, very, very terrible. It's for me. It's showing. It's showing on. So I don't know. I don't know. I think it's a network issue. The online classes there, we have to do all at midnight. Oh. So I've typed it. Those that are not seeing, just go to the chat. It's there. It's in the chat. Just try. I want you guys to try your hands on it so you understand. If you don't understand, I go over before I move on. Yes, so what answers do you have? Let's have it in the chat. For A, what do you have? Okay, Maltiji has 0, 1, and the rest zeros. Yes, who else is having something different? Okay, so you're getting different answers. So let's solve it. Let's solve it. So we have X, Y. The network has started misbehaving. People are not able to connect. Okay, so we have X to E. So how are we going to do it? We are first of all going to take 1's complement of Y. Is that right? And so that's going to be X. That's going to be 1, 1, 0, 1, 1, 1, 0, 1 plus, right, the complement of Y. 1's complement of Y is going to be 0, 0, 1, 1, 0, 0, 0, 1, 0 plus 1. And this is going to give us 1, 1, 0, 1, 1, 1, 0, 1 plus 0, 1, 1, 0, 0, 0, 1, 1. Please, do we understand? Hello, do we understand? Okay, great. So we are going to now do the addition. This will be 0, remainder 1 plus 1, 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 0. Remainder 1 plus this 1, 0. Remainder 1 plus 1, 1. Remainder 1 plus 1, 1, 0. Okay, great. So you see that we have the extra leading carry in front here. Right, and so we are going to get 0, 1, 0, then the rest are all zeros. Great, Maltiti got it correct. Wow, I'm happy. Okay, what did you guys get for B? Yes, B2. What did you guys get? I always like you to show workings because in the exams this question will come. You have a question on complements and you would have to show working. So for B, y minus x, is that right? So what we are going to do is that we are going to take the complement of x. So y is 1, 0, 0, 1, 1, 1, 0, 1 plus complement of x, 1's complement of x. Oh, my Otiti's network is very terrible. She comes and goes like the wind. Okay, so 1001101 plus 1's complement of x would be 001 00010 plus 1. So that when we add, we have 1001101. Okay, so we're going to have plus 0 0 1 0 0 0 1 1 because of the complement. So now what do we have? We have 0 remainder 1 0 remainder 0 remainder 0 remainder 0 remainder 0 remainder 1, right? Then 1. So because there is no extra, it tells us that the number is negative. Is that right? And because the number is negative, we are going to take 2's complement of this, right? This answer that we got. So we are going to take its 2's complement, just like how we did for negative numbers. So how do we take it? We say 2's complement of this number. So first of all, we take 9's complement of this number plus 1. And then subtract it from. So what do we have here? 1 2 3 4 5 6 7 8, right? So let's take 9's complement of this number. What will it be? It would be 0 0 1 1. So 1 1 1 1 1 2 3 4 5 6 1 2 3 4 5 6. Then we add 1 to this. So we are going to get, so plus 1 would give us 1 plus, so that's 0. So 1 0 1 0 1 0 1 0 1 0 1, then 0. So we've inverted it, and now we have our number, but this time this is going to be what? Negative. Is that right? So you just wrap it around, just like how we did it for the decimal, system. We do exactly the same when we are working in complement basis. Please, any question before I move on quickly at the speed of light? I hope you understand. Okay, great. So in your exams, I can be a little bit wicked, and I give you something like using 11th complement, or I can just say use 15th complement, right? Or I would just say use F complement to evaluate 17F minus 15FF. I hope you can do this. So you can write it down and go and try. So in the exams, I can be very tricky. I'm a tricky man. I'll teach you something small, then I'll give you tough questions. Okay. Please, are we good? Let me see your reactions though, so that I know that I'm not alone. That you can be there and I'm not seeing you. Right? Okay. Now, the next thing we have to do is to talk about signed numbers. Signed numbers. So if a number is signed, let's say the number is negative. Let's say we have a number -7. How do we express it in binary? Right? How do we express it in binary? So in binary, what we do is that we reserve the most significant bit, which is the leading digits, right? The most significant bit. So what will be 7? 7 will be what? The number 7 will be 0, 1, 1. Is that right? So the number 7 will be 0, 1, 1. 0, 1, 1. Now, so this is actually the number 7. So there are two ways. What we can do is that we can say, fine, the leading bit will represent the sign. If it is 0, it's positive, that means it's unsigned. If it's 1, it means the number is what? Negative. This one, you get them in the objective. So take note of this. Right now, so if I say I want to write the number 7, then I write, so we know 7 is 0, 1, 1. That's positive 7. So I can say 1, 1, 1, 1, 1 can represent -7. Now observe that 1, 1, 1, 1, 1 actually is the number 15 base 10, which is equal to f base 16. But if we say that this 4-bit number, this 4-bit is actually representing a signed number, you say that one is actually representing a signed number, then it means that it's actually using 3 bits for the number and the leading bit is used for the sign. Please, do we understand? Hello, are we here? Do we understand? Okay, great. So I can give you a question like this. That let's say we are using 8-bit. If we are using 8-bit to store a signed integer, what will be the binary representation for a number -109? Yes, what will it be? Put your answer in the chat box. If we are not doing signed numbers, what will that sequence of bits represent? Please, we understand the question. Just give me the reaction to see that I'm not alone. Makes it feel like I'm the only one and I'm talking to myself. So we have 8 bits. Yes, so what did you get? Yes, what will it be if we are using an 8-bit register to store a number and it's signed? What will it be? Yes, please, let's be quick. Quick. This one, you guys are good mathematicians. You should be able to do this quick. Yeah, so what did you get? Yes, Elijah. Oh, no one is putting something in the text box for me. Yes, Elijah, what did you get? Okay, Elijah, you have your hands up. Can you talk?
Sir, please, I'm asking a question.
Okay.
Sir, please, when we say a signed number, what does it mean? I don't actually get it.
So I was saying that a signed number means the number is having a sign, whether it's positive or negative. An unsigned number is positive. A signed number can be positive or negative. And I'm saying that in signed numbers, like I said, they are not making Okay, so I was saying that in signed number, we use the first bit, the most significant bit, to store the sign, whether positive or negative. Please, do you understand? Okay, so I said that, for instance, the number 7. The number 7 is 1 1 1 1 3 ones 0 1 1. If we are using positive, if you are storing it as a signed bit and is positive, then the leading bit would be 0. So we would have 0 1 1 1. That would be positive 7. Then if it is negative 7, the leading bit would be 1 instead of 0. So that would be 4 ones 1 1 1. Meanwhile, if the number was unsigned, then that 1 1 1 will actually will be storing the number 15. But now, because it is signed, right, it's going to be 1 1 1. So it's very, very important, and you'll be getting some of these in your exams, in your objective. I'll just give you the bit sequence, and I'll tell you that if this bit represents a signed, sequence, what number does it represent? Then I'll give you the number if it is unsigned and a number if it is signed. And you see that most of you will be choosing the number if it is unsigned, and you'll get it wrong. Please, you understand? Great. So, for example, if you take 109, like the question I asked you here, 109 would be 1 0 1 1, then 0 1 1 0. If this number was unsigned, that is an 8-bit number, it will be this. But now we said this 109 is signed. So the first or the most significant bit stores the sign, the 0, the first 0. So because it is storing the sign, it's now going to be 1 1 1 0 1 1 0 1. And this would store the number negative 109. Now, observe that had it not been that this is a signed number, then this number will actually be storing what number? If we are taking 1 to not be a signed digit, but to be a significant digit, you see that it would have a different value. Is that right? Please, do we get it? Please, are we here? So if this number was actually storing, it would be 237. Is that right? 237. Now that is why in C++ and in programming we have two types. We have two types of data. We have the signed int and the unsigned int. Now, can you observe that if we want to store signed integers, the number of values we can actually store halves? Have you observed that? Please, do you understand? Let's say we have a 4-bit space, right? If we have a 4-bit space, 4 bits, so the maximum number we can store would be what? 2 raised to the power 4, which is what? 16. So we can store 16 different numbers. So 16 different numbers that we can store. 16 nodes. But then, like I've expressed to you before, that means it would store between 0 and what? 15. So the maximum number we can store will be what? 15. Right. Now see something very interesting here. This is when it's storing unsigned, but if it is storing signed numbers, then the maximum number it can store will be 1111. But then this one will not be a significant number, it will be a signed digit, right? So this will be the significant numbers, and the maximum number will be what? 7. So that means that this number can be able to store from 7 plus 7 to what? Sorry, it's the opposite. Minus 7 to positive 7. Please, do we understand? Okay, so the signed integer reduces the number and requires more space. In fact, it requires twice as much space to store as much maximum number as possible. I hope we can all agree to that, right? Do we agree to that? Okay, so one thing we take away from this is this thing, and that is why in programming we advise that if you see that you wouldn't need signed digits all the time, declare your variables as unsigned. In that way, you make efficient use of the memory rather than just saying int. So you all, like most of you like that. You just come and say int I is equal to 0. It's a very inefficient way of using memory, right? And even int is a very big number. You should use an 8-bit number. If you are within that space, why should you delegate more space than you would need? Please, we understand. Hey, you shouldn't just delegate more space than you need. Just so in C++, you guys are computer engineers, so I think I have to teach you guys this. It's very important. So in C++, we have access to, so you can initiate an 8-bit memory location, right? And if it is signed, you can say int 8 underscore t I is equal to 0. Please take note of this. If it is unsigned, you can say u int, so u for unsigned. Is that right? So you can say u int 8ti is equal to what? 0. Please, we get it. Similarly, if you have a 16-bit number you want to store, so it's going to be int 16 underscore ty is equal to 0 or some big number. Or you can say u int 16 underscore tx is equal to 2. Now, a 16-bit data, right, 16-bit can take a maximum number of what? Yes. A 16-bit data can take a maximum number of what? Yes. I hope we've talked about this before, right? So you see, you'll be getting more interesting examinable questions. Very, very interesting examinable questions. In your objectives, your objective will be like physics, how you write your physics exams. What's the physics? Yes, who has an idea? Yes, what will it be? Can you put it in the chat? You guys are not revising your notes at all. Okay. Media, I've told you. I've told you. A 16-bit. No, 16 bits. Yes, somebody said 15. How 15? 25535. 2 raised the power what? 16. You guys should really go and look at your notes well. A 16-bit data can store 255. That is unsigned, if it is unsigned. If it is signed, remember that if it is signed, it stores half of this. Is that right? So if it is signed, if it's unsigned, so let me come to the unsigned before we come to signed. Unsigned. Unsigned is 2 raised to the power 16, right? So that means you can store 2 raised to the power 16 different numbers, including 0. So the maximum would actually be between 0 and what? 65,535. Is that right? Now, if it is signed, what will it be? Yes, what will be the range if it is signed? And these are the questions you'll be getting for your objectives. Okay, great. Somebody said the right thing. So that means it will store from -32767 to +32767. Now somebody is saying that, oh, these are theory, we don't need it. Fair. This is not theory, you really need it when you're doing systems engineering. When you're doing large systems engineering as a software architecture, a writing architect, especially for softwares that run at elevated privileges on the CPU. You know, we have the CPU stack and we have levels of privileges. Some that runs on the BIOS level, right? And drivers. I believe that you guys are going to be great guys in the future. You're going to be making electric vehicles, right? When you're making electric vehicles, these things become very, very important because you're going to build an operating systems for them. And most of these operating systems that are around that you will likely adopt, this is how they develop it. And they design everything, they optimize every single bit for it to take the right size it needs to take, right? And so you need to know all of these things. You need to, as I say, like you need to know them and you need to be very, very good at it. Please, do we understand? Okay, so you can also define a 64-bit data with uint 64 underscore tm is equal to 0. Then you can say int 64 underscore tn is equal to 0. So in your exams, you would be having these questions there. And you see, I'm just giving you your questions before you even come. Yeah, shouldn't be doing that. I'm doing this because I won't spare you. Like I won't consider you after I mark your exams. So I don't want you guys to fail. So you won't come and tell me that he gave us things he didn't teach. Any question before we move on? So in your exams, when I give you these questions, I hope you can do it, right? Now, lastly, before we close, we are going to discuss what we call parity bits. So these are things you need to know. Now, a parity bit is something we add to a sequence of bits to help us know if during the process of data transfer there was an error. Now, there are two types of parity bits. we have 1, so parity bit, parity bit, parity, parity bit. So there are 2 types. We have the even parity, then the odd parity. Now, so my screen is not updating, so you'd have to make some notes on your end. Now you say even parity, this is what we mean. I can say I'm transferring the bit sequence. I can be transferring the bit sequence 0, 1, 0, 1. Let me just use 108 for it. Okay, so where is it? Where is 109? Let's say I'm transferring let me use 0, 1, 0, 1, 1, 1, 0, 1. Now in parity bit, I'll just say, okay, how many count of ones are there? So that one, it depends on you, the designer. You choose what you want. So you can say, okay, how many ones are there? So I have 1, 2, 3, 4, 5. In even parity, right, I would add, so the first bit here, I want to have a certain even number of bits. So these are 1, 2, 3, 4, 5. So that means there are 5 ones, which is odd. So if there are 5 ones and it's odd, in parity bit, I'll just add 1 in front. If it's 5, then it's odd, I'll add 1 in front, so that the number would become even. The number of bits would become even. Right. Now, if I transfer it to the terminal location and we both agree that we are doing even parity and the order of parity we are doing, then we count the number of ones and it's not even, that means it's odd. It tells us that 1 bit, at least 1 or more bits have changed when we were transferring that data. Then we will ask the sender to resend. Please, do we understand? Okay, so that is the even parity. You add to make it even. The odd parity is the other way around. We can have an even parity 0, 1, 1, 0. Then I will say that I want to add something. Yes, Elijah, your hand is up. Maltiti's hand was up first. Yeah, Maltiti, let's talk.
Yeah. The one, when you are to add it, is it in front of the 0 or you remove the 0 and put it there?
So usually it's you, the designer. You can add it at the end, you can add it in front. But for a convention, a good convention is that we've reserved the front digit, the most significant bits for signed, interchanges, right? So you are the one designing the system, that's it. So you are the one designing the system. So you can say that this is my system. The whole world, everyone is putting their even parity in front or at the back. Me, I will put my even parity in the middle so that I will encode it. Then no one can see. I just want to keep it my secret so that people can't break into my secret. So you are the one who does what you want. But the whole concept is that you add an extra bit to make the number of ones in the bit even or odd, so that if we receive it and the number of bits is not even, if you agreed on even, then it becomes odd. That means at least 1 bit has changed when you were transferring that data. So you wouldn't even attempt to encode it or reconstruct it. You would just tell the sender that, guy, the data you sent has appeared to be corrupted, so resend. So you see, it's a very, very simple way of error detection, right? Very, very simple way of error detection. So it helps you detect what we call odd. So it helps us detect odd number of bits changes. Yes, someone else's hands is up. Please talk. My time is up.
Please, is it that you are changing the 0 to a 1 or you are adding 1 in front of it?
So you are changing the one in front of it or the one behind it to a 1 so that you make the number of ones even or odd based on what you have agreed to do. So you're just flipping it. It's not like you are adding. Yes, so that actually changes the true value of the number. But because you know what you're doing, when it comes back, you just reverse it to get back because you've already agreed. So when it comes to you count, you make sure that, oh, that means the parity is correct. Okay, now let's reverse it back to the number that it was before we did that change based on what we've agreed on. So it's a form of an encoding, right? We call this a public key cryptography. That one is not hashed with a private key that you need a private key to decode. We know it. The private key is with us. So it's just one-way cipher. Please, we understand.
Yes, please.
Yes, someone else's hand was up. Then we also have the CRC codes we add and all of that. Now, one thing that we very much do is that, so let's say that I'm transferring this data to you. I, the designer, so I'm sending this data to you. I, the developer, can say, okay, to encode my information, I want to encode my information. So I would add this number to it so that it changes. Now, if somebody is able to intercept the communicate, then he decodes it. Number one, the person doesn't know the parity bit we are using, whether it's even or odd. Number two, the person doesn't even know that we've added, we've added this number 101 to it. So he would decode it with everything included, and he wouldn't actually get a true idea of what we actually sent. Right, and that is a form of a lightweight encoding that we can do. You see, in Ghana, our designers don't do all of these, right? They will just, if they don't even know these things, our designers don't do digital logic, so they just focus on the Arduino, right? Now in the industry, if you focus on Arduino, you won't survive. Is that right? So you need to have a very good grasp of data logic design so that you can understand how things work. Yes, Elijah, please be very quick. I have to be leaving for the next class right now.
Yes, sir. Please, with the parity bit, in case someone enters into your system, does the person takes over your system before you are able to detect it and then use your parity bit to, counter the person?
So a clarification is that parity bit is not a cybersecurity, tool. No, we don't use it for cybersecurity. So parity bit will not tell you somebody has broken into your system. You will never know. Parity bit is just for one thing, to tell us if the data that we were transferring changed. So it's for error detection. We just want to see if this data that we have received from Akwasi, is it correct or it changed? There is noise around us. So it could happen that on the way that it was coming, there was a change or two. Is that right? So parity bit tells us whether a change happened or not. Please, we understand.